Today, I'm very pleased to welcome Adam again to present the first paper today.
So I'll be talking about, thank you, Chris. First of all, let me thank you for your patience in listening to me so much and putting up with me. And let me sort of repeat the request yesterday that you keep your questions coming and make this as interactive as possible. So I was going to be talking about algorithms for convex optimization subject to differential privacy. And this is in some sense a continuation of the tutorial. I'll be mentioning some very recent results, but also trying to kind of cover a body of work of mine and others that has gone on for the last few years, and just give you a sense of of the ideas and the techniques that are involved. And again, I'm happy to take questions as we go. Okay, so really this is a kind of focus of this talk are the computations that underlie a lot of statistical inference. And just to give some examples, first, one sort of classic example. Oh, sorry, my animations are out of order. Let me make sure I get my pictures up. There we go. Okay, so an example, a classic sort of statistical computation given a data set is to compute the median of a data set. So this picture is, giving us the median of some, density function. On the line, but of course the median makes sense in higher dimensions also. So it's the, roughly speaking, the Euclidean median is given a collection of points in the plane. It's a point that minimizes the sum of the distances to the points in your data set. Okay. Ordinary least squares linear regression is another sort of type classical computation that's done where you're trying to find a line or a hyperplane that fits a given collection of data points as well as possible. Logistic regression and support vector machines are particular sort of ways to fit a linear function to data in as well accurate a way as possible according to some measure of accuracy. And in all these cases, actually, the natural estimator, the natural thing you want to produce as the outcome of your computation, is the result of minimizing some loss function, and that in all cases, these cases, the loss function has this additional property that makes it relatively easy to work with, which is that the loss function is convex, so it has a nice bowl shape to it. And I'll say more about that in a second, but roughly, at some level of abstraction, you've got some loss function that depends on your data, and also and is a function of some parameter theta, which could be a single real number or a vector, and you want to find the parameter theta that minimizes this loss function. So somewhat more abstractly, we've got a data set. This is following up on our setup yesterday. Our data set is a collection of points in some universe. We'll call it U. There are n of them. And now we're trying to find some parameter vector theta. And theta is limited to theta lives in some set C, which is in real space. And that set C could be all of real space, or it could be constrained to some subset, depending on the particular problem. So if we had a constraint, here's my constraint. And we're going to look at loss functions that are decomposable, meaning that they can be written as a sum of terms, one of which, where each term depends on only one data point. Okay? So this is what, so a loss function is decomposable if it can be written in this form. It's the average of a bunch of terms like this. And here the assumption is that, as I said, where convexity comes in is that we're going to assume that the dependency on this parameter is the function, as a function of this parameter, these terms are all convex, which means that, as a quick reminder, what makes a function convex is if you take any 2 points, any 2 arguments to the function, and draw the line that connects the corresponding points on the graph of the function. Everything, the function always lies below that line in between those 2 points. Another equivalent definition of convexity, which we'll actually kind of try to use more or less explicitly in the talk, is that if I take any point on the graph of the function and I can find some linear function which is tangent to the graph at that point and which lower bounds the function everywhere. Okay, so essentially what convexity means is that in one dimension it means that if I sort of start at a point and draw a line whose slope is the derivative at that point, then I'll get a line that's a lower bound for the function. And in higher dimensions, you'd replace the derivative with a gradient or a subgradient. But in any case, it always means I can sort of always find a linear lower bound for the function. That's what convexity means. So our assumption is that the loss function is convex, and also that the constraint set, the set of parameters that we're willing to consider, is also convex, which means basically means it doesn't have any holes in it. Okay. And as I said, and I'll sort of spell out the loss functions explicitly on the next slide, but all those examples I gave you are examples of minimizing convex loss functions. Okay, so the thing we're going to be after is minimizing. So we're going to be trying to kind of look at algorithms for finding either minima or approximate minima to these types of functions. And when we're giving approximate minima, which is going to be the case for differentially private algorithms, the measure of quality of our solution is going to be something which we'll call the excess risk, okay, which is the difference between the value of the function at the true minimizer and the value at of the function at the point we finally output. Okay, so if we output something that is not the true minimizer, then our measure of quality is the difference between those 2 values. Okay. And actually, in statistical context, there are really 2 notions of excess risk that matter. There's how well I do on the function I have that really depends explicitly on the data set, and there's how well this parameter I output would do on other samples from the same population. So if I think of my data set as being drawn from some larger population, what I might really be interested in is some sort of measure of population risk. How well does the thing I do, how well does it do relative to the best parameter for the population as a whole? Okay? And actually, this is the thing in many contexts we'd really like to reason about. For this talk, I'm not going to really draw the distinction between those two notions of risk, except perhaps near the end of the talk I'll mention about. But for now, we'll just pretend that all we care about is the what's called the empirical risk, so the risk on the data set we have. Okay. So just to go through some examples. So the median is an example of this. So for the median, as I said, in real space and arbitrary dimension, there's a well-defined notion of a median, and it's a point theta that tries to minimize the sum of the distances to the points in the data set. Okay, this actually has a very natural interpretation in the plane. If I were to take a flat table and drill a hole at the location of each of my data points, and take a bunch of, I could imagine taking n strings that are tied together in one knot, and dropping a string through each of the holes and attaching a weight to each of the strings, and then letting go of the knot. And where the knot would stop, that is this median in this sense.
The median should be L1.
So well, this is the Euclidean median. So in
one dimension, it's the mean that minimizes.
No, so there's no, notice there's no square here.
Minimizing square of a function, the function is the same.
No, but the sum of squares is not the same. So if you minimize this, so this is a good point. So actually the mean and the median, of course, are different objects. So the median in one dimension, let's provide, in one dimension, the median is the point, is a valid median is a point that minimizes the sum of all the distances to the other points.
He says this is L1, so there's no disagreement.
And in L2, no, I meant L2 here. But, I mean, you can define it with L1. If you define it with L1, you're taking...
Positive part of the square root, right?
So let's, okay, no, this is important that we understand what the, okay. Let's make sure we understand the example. Yeah, so here xi is a point in is in d-dimensional space, right? So xi has d coordinates, theta has d coordinates, so this is a vector of d dimensions. This is its Euclidean norm. That's so if I were to minimize the sum of the squares of the Euclidean norms, that would also be a convex minimization problem. That would be the mean. If I minimize the sum of the norms themselves, what I get is the median. Okay, and they correspond to different statistical contexts, right? So if I was thinking of this as a maximum likelihood estimator, the Euclidean mean is a maximum likelihood. The mean is the MLE for, say, the mean of a bunch of data that I assume is drawn from a Gaussian distribution. This is the MLE for data drawn from, say, a gamma distribution or some other spherically symmetric distribution that's not exactly normal. So one of the things that's going to make the median interesting from the point of view of privacy is that the effect of a given data point is very different on the mean and on the median. So they're really different computations. So even though they have a sort of roughly similar interpretation and they may at first appear to be kind of quite similar, the techniques we'll use to reason about information loss when we're trying to release these are actually going to be different. Sorry, I didn't really mean that to take so long. Okay, linear regression. So ordinary least squares linear regression. You've got, you think of your parameter vector as mapping a feature vector to a real number, and you're looking at the square difference between the real number and the dependent variable you're trying to fit to. Logistic regression is another example. It's sort of a similar thing where your loss function is given by this logistic loss. And a support vector machine is yet another similar example where the loss function is given by this hinge loss, where a hinge loss is this sort of piecewise linear function that is sort of 0 on half the line and has slope 1 on the rest of the line. Okay, so the point is that all these examples sort of fit in the same broad framework of convex optimization. So if we give algorithms for solving sort of general optimizing decomposable loss functions in general, then we in particular give algorithms for all these problems. Okay. Any questions? All right, so why should we care about privacy in these computations? So again, going back one slide, what we're interested in is finding, we're given a data set, we're trying to solve this optimization problem, this potentially high-dimensional optimization problem. And what we're interested in is producing some output that is close to the true minimum for this loss function. Okay? And sort of a natural question at this point is why do I even have to do anything? Why can't I just output the minimizer for the loss function? Okay, why this is some aggregate computation. Why is it that I need to worry about privacy at all So yesterday we saw some examples of kind of relatively simple statistics that could potentially leak a fair amount of information, relatively simple aggregate statistics that could potentially leak a fair amount of information about a data set. And these types of convex optimization computations also have this feature that they can leak a fair amount about individual points in the data set. Okay, so a very simple example is if I take the median in one dimension, if I think of it as a sort of an optimization problem, the loss function I'm trying to minimize is the sum of these little wedge functions. Okay, so it looked like for 3 data points, the loss function looks something like this. And in one dimension, the true minimizer of the true median is essentially always a data point, at least when the number of data points is odd. Okay? And so it's always giving me one of my data points kind of in the clear. And now in sort of at first glance, that might not be such a big deal, except for the fact that, because in one dimension, this is just one real number, although with high precision, that already can be a big problem. But actually, this issue can arise also in higher dimensions. And again, in higher dimensions, it's often the case that the true minimizer is one of the actual data points that you care about sort of exactly. And so if you're outputting the true minimizer, very often what you're outputting is one of the data, the data for one of the people in your data set sort of completely in the clear. Also, as I mentioned yesterday, for the support vector machine, which is another kind of commonly optimized loss function, the dual form of the solution, which is sort of the standard way the solution would be reported, includes a certain number of data points in the clear. In dimension d, it includes d plus 1 data points, each of which is a vector of length d, sort of in the clear. Okay. And also, a number of the reconstruction attacks and the membership attacks that I mentioned yesterday work equally well based on the outputs of various convex optimization problems. And in particular, some of the attacks that Cynthia will mention in her talk later today work just fine based on these outputs. So even though this is the result, the thing we're doing is the result of some sort of fairly complicated computation, it's often relatively easy to figure out very specific things that this tells us about individuals in the data set from these outputs. Okay. And so, sorry, this is my thing is before. So what we're going to do is we'd like to solve this problem subject to some rigorous reasoning about the amount of information that's leaked about any one individual. And this problem, sort of the way I formulated it, was posed in a paper of Chowdhury, Montalani, and Sarwate, and the journal version was 2011. And their requirement was that you find algorithms for solving this problem where the algorithm that produces this parameter estimate theta hat is itself differentially private in the sense that we discussed yesterday, meaning that when I change any one data point in the data set, I can control very carefully the change in the distribution on the parameter estimate theta hat. So this will allow us to limit the information leaked by the solution about any one data point. And in order to sort of do this, in order to do this meaningfully, we need to somehow limit the amount of the influence that any one term can have on the optimization problem, right? If there's one term that totally dominates, if there's one person who completely dominates the optimization problem, if there's one of these terms that's much larger than all the others, then we're not really going to be able to do anything meaningful. We need some sort of measure of control. And for this talk, the assumption we'll make is that the contribution of each individual is bounded in the sense that the little loss function is Lipschitz, meaning that the gradient of that loss function at all points I know a bound on its norm, an upper bound on its norm. Okay? And the exact upper bound isn't really going to, the nature of the upper bound isn't going to play an important role in the talk, but I just want you to be aware it's there. So we're going to have to assume that. And all the problems that I mentioned on the previous slide, in particular, have some naturally come with this assumption sort of built in. They satisfy it by definition. Okay, so there are a number of algorithms out there in the literature that have been come up with, and the people. Sorry, that was poorly said. There are a number of algorithms that people have designed over the last few years that use randomization in different ways to produce an approximate solution that is hopefully close to the correct one. And I'll kind of try to illustrate each of the ideas behind each of those algorithms, and just sort of explain how some of the tools that came up in the tutorial yesterday can be applied to this problem. And I'll also spend some time on what we know about the best possible bounds we can get on that excess risk measure that I was talking about earlier, and lower bounds that show, basically telling us when the bounds we know are optimal. And there's an open question there that I hope I'll get to. Yeah?
Can I ask you as a favor to most of the rest of us to put the citations, when you put the citations in some standard scientific citation format, so the rest of us can find these papers?
Yeah, yes, you can. It's a bad habit that I should break. I'm not, but it's one I should break. Yeah. Okay. Yes.
Thank you.
Okay. One thing I'll say is that if you take my most recent paper on this topic, you will find these acronyms in the reference section, and you'll be able to look them up. But that's really not an acceptable answer. I understand that's not what you're asking. So these are just authors' last names. Yeah. there's a cultural issue here too. Yeah. But this is a bad habit that I should get out of. Okay, so as I said, what I'd like to do is just kind of start by giving you a sense of some of the different algorithms people have proposed for this problem and how they work, and what the idea behind them is, and why they're kind of not insane things to do. Okay, so one of the simplest and nicest algorithms for this problem is called the objective perturbation algorithm, and this is due to that paper I cited earlier of Chowdhury, Monteleone, and Sarwate. And the idea is actually very simple. What they're going to do is they're going to solve some optimization problem exactly, which is not the optimization problem given to them by the data, but a related optimization problem. And the way they'll find this related optimization problem is they're going to pick a random vector, which is, some Gaussian distributed vector. This is actually a version. The version of the algorithm I'll give you comes from a later paper of Dan Kiefer and mine and my student Amardeep Thakurta, but close enough. So we're going to take a Gaussian random vector that's Gaussian distributed, and instead of the standard version of this optimization problem is I would find the point where the gradient of the loss function is 0, and that would be the minimum. And here what I'm going to do is I'm going to solve a related equation. I'm going to find a point where the gradient of the loss function is equal to this random vector b. Okay? And so the variance of the entries of this random vector is going to scale with 1 over epsilon, or the variance will scale with 1 over epsilon squared, where epsilon is this privacy parameter we were discussing yesterday. Okay. Yeah, okay. So here C is some constant that depends on parameters of the problem that I didn't fully flesh out. So
that solving a score function to not zero, something that
to something that is not 0. And actually, I realized that I've normalized things differently. So the variance of the noise I add actually goes, the standard deviation goes to 0 with n in the normalization I had on the previous slide. Sorry, there's a disconnect between the two slides. So that should be, there should be an extra factor of n in there where n is the size of the data set.
Does C depend on the loss function?
And C here, yeah, so the constant that goes up here depends on the bound you have on the gradient of each of the individual terms. It depends on the smoothness of the loss function up to a point. So it's actually kind of it's a minimum of a few different things, or sorry, a maximum of a few different things, and I didn't really feel like spelling it out. But yeah, so it's going to depend on various various things I need to know about the loss function. So it's going to depend on smoothness. It's going to depend on the gradient bound I have on each of the individual terms, and it's going to depend on some measure of strong convexity of the loss function. And I'm sort of when I say a cheat here, I'm actually cheating by ignoring one additional requirement, which is I'm going to have to, in order for this algorithm to be differentially private, I need to assume that there's this loss function can't just be any convex function. It has to be very slightly strongly convex, and you can sort of enforce that by adding a regularizer to the loss function that doesn't really significantly affect the outcome of the optimization. But yeah, so I'm sort of brushing a number of things under the rug, and that's just because I don't think the details are that relevant here.
Important for the least squares application.
Actually, no. So in the least squares application, very often you can get away without that extra regularizer, depending on.
Gradients not for
So in the least squares application, you need to bound the parameter vectors.
So if
Yeah.
you don't do it with the regularizer, then you have to do it ad hoc. Okay.
Mhm. Yeah. Right. So what you're doing is instead of solving this score function where for the gradient to be 0, you're solving it to some non-zero term. And the point is that if I think of the loss function as the average of all of those little loss functions, then indeed the variance of this additional term goes to zero with n. And so at least for large data sets, it has a very small, it induces a very small perturbation on the actual thing you output on the minimizer. And in general, actually, this method actually does really well experimentally when you have a nice smooth loss function. So for example, for logistic regression, it works very well. And one of the reasons it does so well is that if you have a data set where the minimizer is really well defined, if you have a data set where as you go away from the minimizer, the loss function increases steeply, then this additional perturbation has very little effect. On the other hand, it gives you sort of some meaningful privacy in the worst case, because if you do happen to have a data set where the minimum is sort of not especially well defined, where there's a large and shallow basin, then what it basically gives you is a random point in that big, wide, shallow basin instead of the exact minimizer. And that's because when you've got that sort of wide, shallow basin, you're in a situation where a single data point can give you can have a lot of effect on the actual location of the minimizer. Okay, so this is one idea that people have used successfully for this type of problem. And generally, it's for loss functions that sort of satisfy its requirements, it's the one that performs best experimentally.
I think.
Yeah. Oh, sorry, Becca. Yeah, I didn't.
I have I think a very naive question.
Sure.
When you say it does very well experimentally, how does it perform? For example, is it very sensitive to the choice of, for example, C and epsilon an epsilon?
So what you'll get is I should. This is maybe. What I was hoping to do was have some evidence to back it up. And let me explain. So what's going to happen is as epsilon decreases, it's going to give you worse and worse solutions, right? And the other thing that's not obvious here is that for most, though not all problems, as the dimension increases, it will give you worse and worse solutions. And that corresponds to the fact that usually as you sort of consider higher and higher dimensional problems, those things like the bound on the gradient, for example, become worse. I mean, larger. And so you end up having more perturbation introduced. And again, we know that to some extent that's necessary. So another method that is tricky to implement, and I'll explain why in a minute, but does reasonably well, is to use this exponential sampling idea that we talked about yesterday. Okay. So this is the idea from of McSherry and Talwar I mentioned before, and the application in this context came from a paper of mine. But the idea is that I'm going to sort of remember I'm trying to optimize this loss function. I'll use the same idea we did yesterday, which is that if I'm after I want to create some distribution which is concentrated near the true minimizer. And the way I'm going to do this is I'm going to assign weight. I'm going to find a distribution on the entire set of possible thetas, that constraint set C, which might be the entire all of real space. And the way I'm going to do it is I'm going to assign exponentially more weight to points where the loss function is lower. Okay, so I'm going to find a probability distribution whose was such the probability of a given vector theta, the density at a given vector theta is proportional to e to the minus epsilon times the loss at theta.
You make it a maximum likelihood.
And essentially what this is doing is, again, this is not exactly finding the maximum likelihood estimator, because what I'm going to output is a sample from this distribution, right? So what this is doing is this corresponds to roughly some, in this case, not quite well posed Bayesian inference problem. So there's a way to sort of think about this as outputting a sample from some posterior distribution on theta given the data you have. Okay? You have to be a little careful because we've messed with epsilon and there's no explicit prior, although you could put one there if you wanted. So it's not quite a well posed. It doesn't quite fit the framework I just said. It doesn't quite match, but it's very close. And roughly speaking, it corresponds to outputting a posterior a sample from the posterior distribution on theta, where I've sort of squashed the likelihood function by this factor of epsilon. Okay, so in some sense, again, sort of limiting the influence that any one data point can have on that final probability distribution. And I should mention that this sort of Bayesian perspective on it was formulated explicitly and very nicely. The connection to Bayesian reasoning was pointed out nicely in a paper of Yusheng Wang, Jing Lei, and Steve Feinberg, not necessarily in that order. I forget the author order.
Wang is certainly the first author.
Yeah, so Yusheng Wang is the student. I think he went first. But yeah, so I'm bad at remembering author orders, again, for cultural reasons. All right, so okay, so this is another perfectly reasonable thing to do, and you can actually reason very precisely about how well this is likely to approximate the true minimizer. And you can actually show that at least sort of up to asymptotics, in the worst case, it behaves very, very similarly to that the argument that objective perturbation algorithm I had on the previous slide. And actually, in some cases, they even correspond to exactly the same algorithm. There are cases where they kind of align exactly. But yeah, basically, you can analyze this by to analyze the utility. What you do is you sort of chop your space into regions corresponding to level sets of the loss function. And roughly, you know that theta is uniformly distributed, roughly uniformly distributed within each of these regions. And then if you can control the relative mass of each of the regions, and you can argue that the first region has more mass than the others, then you can argue that that's the thing you get with high probability, and you wind up close to the true minimizer. Okay, so the hitch really for this method is that sampling from this, constructing and sampling from this distribution computationally can be a little tricky. So in general, it can always be done in polynomial time, but and one can always, there are nice, easy sampling methods that, as far as we know, always do well for these types of loss functions, for these types of distributions, but getting like a worst case analysis to show that you're really sampling from exactly this distribution, that is kind of tricky. But I would say for all practical purposes, sampling from these things is not too hard. Okay, maybe I'll come back to these in a minute. Okay, so let me explain another kind of class of approaches to this problem, where the idea is to take an iterative method, an iterative optimization technique that works sort of regardless of privacy, that was designed just for optimizing these functions non-privately, and get a differentially private version, not by sort of perturbing the final output or the loss function, but by introducing randomness at each stage of this iterative algorithm. Okay, and the example I'll give is a noisy stochastic gradient descent. So stochastic gradient descent. Okay, so let's recall what gradient descent is first. So gradient descent is an optimization technique where I start from some arbitrary point, theta. I compute the gradient at theta, and I take a small step in the direction away from the gradient to take me to lower on the loss function. Right? And under various conditions, gradient descent is known to converge. For convex optimization problems, we know a lot about how gradient descent behaves. Okay. So I guess maybe I should mention one of the reasons why convex loss functions are so widely used, this class of loss functions comes up all the time, is that just by nature they always have either a unique minimum or all the minima are all stuck right next to each other. So what you cannot get with a convex loss function, you can't get weird local minima. Right? Because then if I look at this point and I try to take the line that is tangent to the graph of the function at that point, I don't get a lower bound on the function. Right? So convex functions are those where basically greedy algorithms, very simple greedy algorithms for optimization actually work. That's roughly a definition of convexity. And so what we're going to do is take one of those and make it differentially private. And essentially, we're just going to run gradient descent, but instead of using the exact gradient of the loss function at each step, what we're going to do is use some approximation to the loss function. And we're going to there are going to be two kinds of approximation going on. The first kind is due to sampling. So what we're going to do at each iteration, we're just going to pick, rather than evaluating the gradient at all possible points, we're just going to pick one point and evaluate the gradient at that point. And if we make sure to pick a random point at each iteration, then what we know is we're getting an unbiased estimate of this average. Okay, just by sort of standard sampling argument. In expectation, what we get is this average. And then we're going to take one point, compute its gradient compute the gradient for that data point, and then add some kind of noise to that gradient. And then finally, then we'll update our parameter. So we've got a parameter estimate theta of t minus 1. We'll get a parameter theta of t, we'll update it by subtracting off some multiple of this noisy gradient. And then we might have this step where we might have to project ourselves back onto the constraint set. So if we've got constraints on our parameters, then when you take a step in the direction away from the gradient, you may leave the set of feasible points, and you have to bring yourself back. So that's what this projection is for. Okay, and so this, in a nutshell, this is the algorithm. And again, the amount of noise we're going to add is going to be some function of kind of a bunch of parameters of the problem, and I'm not going to spell it out. And it's, in fact, the type of noise we add is not even, it's zero mean, but it's not independent of this object. It's it's kind of a complicated noise distribution, but well, you can think of it as roughly approximated by Gaussian noise. And this idea was evaluated, actually, first proposed by, in a paper of Ollie Williams and Frank McSherry back in 2010, or some variant of this idea, and explored more carefully by Song Chowdhury and Sarwate. And then we had a paper where we sort of further improved it and also gave an analytical bounds on its performance. But maybe one of the interesting things, instead of, I'm not going to dwell on the attribution, one of the interesting things here is that there, as I said, there are sort of two sources of randomness. There's the fact that we're sampling a single data point to compute the gradient, and then we're adding noise. And it turns out that both of those contribute to the privacy analysis. You can sort of, you really get a concrete benefit from each of those steps. And the reason that this is a good thing to do is that computationally it gives you a method that's much more efficient, because at each iteration of the algorithm, you only need, because you're only sort of touching one data point at any given time, the computations you do are relatively simple. Okay, so sort of pictorially what's going on is this. We've got some loss function, which is the the loss function we're trying to optimize. We've got some constraint set. We've got some current parameter vector theta t. We're going to pick a random data point, little x, and look at the contribution to the loss function provided by little x, and then we'll take a step away from the gradient at that point. And if that takes us outside of the constraint set, then we have to project back into the constraint set. Okay, and we sort of keep on repeating that operation over and over, and eventually, after enough iterations, we get a very good answer. So the sort of dirty little secret is that in order to get the theoretical bounds on the accuracy, you need a really huge number of iterations. You need about n squared iterations, which is actually not that great. Although it turns out that empirically, a much smaller number of iterations does just fine. You don't really, for most of the things most of the data sets we tried this with, after 20 or 30 iterations, you didn't really get much further benefit. Yeah.
So if you have some time, could you comment on the application of this technique to the multi-party secure computing model that Shukri and Shmatakov did? Your thanks. So you might not know exactly what they did, but you were thanked for contributing this algorithm to it.
Yeah, that's a good question, because I don't remember what's in their paper.
So they do a neural network deep learning model with each of the parties doing their own computations and contributing the update to the gradient from the noisy stochastic descent algorithm processed through a combination of the sparse vector technique and
right. So I think my contribution to that was mentioning the word stochastic. and I think the fact that I was acknowledged in the paper reflects only the fact that they got this idea via, like, my contribution was saying you should really look at the stochastic gradient descent methods because they'll save you a lot of time.
But in contrast to runs on experimental data, it's been actually run on real data in a much more challenging environment than just a single user. So that's a
Right. So that's a very the downside to that algorithm is that we don't really have any analytical understanding of what's leaked by the algorithm in the Shokri-Shmadikov. So I think you can argue that sort of individually various updates that they release are basically differentially private, but the kind of final guarantee they get, if I remember correctly, is not that strong. And that's partly because they're up.
I would appreciate a careful reading by somebody from your class of computer scientists, because that's not what the claim is.
I mean, okay, I'm sure, like, okay, yeah, maybe we can talk about it offline. I don't want to spend.
The n-square iterations are required for privacy or for?
No, just for the accuracy bound we have, the analytical bound we have in the paper, you need n squared iterations, and that's actually not, this n squared doesn't come from, this n squared thing is actually, you get that for the non-private version of gradient descent also, in the sense that over t iterations, the standard, under general assumptions, the standard kind of convergence guarantee that you get for gradient descent is you get an empirical risk of about 1 over square root of t, where t is the number of iterations. So in order to get the optimal risk bound, which is 1 over n, you need t to be about n squared. Okay. As I said, I have not, so that's the worst case bound, but in practice you can get away with far fewer iterations. And maybe I'll come back to this, but like as with a lot of the methods I discussed yesterday, I think there is still a lot of engineering to be done and sort of fine-tuning of figuring out the best way to actually really use these algorithms in sort of general settings in a way that adapt to the data set you have and really give you the best possible answers. Yeah. So I'm not going to dwell on the analysis. I just wanted to describe the idea. And there's another class of iterative algorithms that was exploited for differential privacy that have a sort of a similar flavor, but it's not gradient descent. They're variants on an algorithm called the Frank-Wolf algorithm. And there the idea is that, so this works very well for certain types of constraint sets on your parameter vector, especially for cases where the set that you're optimizing over is a polytope with a not too large number of vertices. Okay, so for example, so this is Frank-Wolf, the Frank-Wolf algorithm, and it performs very well for certain types of constraint set. And one constraint set that comes up a lot is when you're optimizing over the set of points in real space that are bounded in the L1 norm. So this is the constraint set that comes up, for example, in the lasso and related models for sparse regression. Okay, so if you don't know what the lasso is, it's a specific optimization problem. Again, you're solving ordinary least squares, but rather than allowing for an arbitrary parameter vector, you restrict yourself to parameter vectors that have a bound on the L1 norm, a relatively small bound on the L1 norm of the vector. And it turns out that when you optimize over this set, you commonly wind up with solutions that are sparse, that have relatively few non-zero terms in them, and that is good for various reasons. But it actually helps us for privacy also. So there was a nice paper by Talwar, Thakurta, and Zhang on how to exploit this sort of additional structure, and they do so by modifying this Frank-Wolf algorithm. So again, it's an iterative algorithm where you start with some parameter vector at time t, you compute the gradient of your loss function at that point, and now you want to kind of travel in the other direction, and so but rather than just taking a step in the direction of the opposite to the gradient, what you do is you're going to follow this line as far as you can in your constraint set. Here, let me draw it a little differently. And you're going to find the most extreme point in your constraint set that you can in this direction. So you're going to go as far as you can in this direction in the constraint set. So in this case, you'd sort of look at this point over here. And now what you'll actually, to update your parameter vector, you'll take a step in the direction of this extreme point. Okay. And how far you go in that direction is, again, sort of some parameter of the algorithm that has to be tuned. But this is the idea you do at each iteration in the algorithm. And the point is that the computation of this most extreme point for some constraint sets is very simple. In particular, the nice thing about this constraint set is that even in 100 dimensions, there are actually only 200 extreme points for this constraint set. And so you're optimizing over a relatively small set. This optimization step that you do at each iteration is very simple in that case. And that has benefits both for computational efficiency and, again, for privacy, because it allows you to limit how much you need to reveal about your data at each iteration of the algorithm. Okay. So in this paper, they show that you can take advantage of this to get much tighter bounds on the performance of on the accuracy of the algorithm in cases where the geometry of the constraint set is somehow confined. And it turns out, so one case that their algorithm works well on is when you have relatively few extreme points in your constraint set, and there's some more general theory of like which constraint sets are amenable to this. That's based on what's called the Gaussian width of the set. I'm not going to go into. Okay, so just to wrap up in terms of what we can say about the actual performance of these methods in the worst case. So what we can get is that under epsilon 0 differential privacy, we can get an excess risk that goes to 0 with n that goes to 0 with n, but you pay some price that depends on the dimension. So you need the ratio of the dimension and n. You need the ratio of the dimension over n to go to 0 to get a good risk bound. And for epsilon delta differential privacy, you get a sort of a stronger guarantee, which goes to 0 as long as n over the square root of the dimension goes to 0. Okay, so these are the types of bounds you can get for the types of algorithms I've been discussing. And these are, as I said, these are worst case bounds, and they're bounds on the empirical risk. It turns out, on typical data sets, they seem to do better, although we don't necessarily have a really good understanding of when and why. And also, the other thing is if what you're really concerned with is population risk, which is the thing that normally concerns you in statistical settings, then you actually can get these bounds are actually well below the kind of inherent statistical risk due to sampling, and so in most settings, these are essentially asymptotically match the performance of the best non-private algorithms. Okay, there's an open question there for very large dimension. Especially for epsilon delta differential privacy, there's an interesting open question about whether or not for population risk this square root of d function term is necessary. It may be that it can be removed entirely. And then it turns out one can come up with lower bounds that match, oh, sorry, this is, you know what, let me not talk about that. Sorry. That's for another class of loss functions. I'm not even going to bother to go there. Yeah, so it turns out that if what you're concerned with is empirical risk, then you can come up with lower bounds showing that one cannot do better than this. And that's because of these membership test attacks that Cynthia will mention. Okay, so I'll stop there, and I think I've got a little bit of extra time for questions, or we can just stop there. Yeah, thanks.
Great. Thanks very much. Adam.
Any extra questions?
Do questions.
Yeah, you'll see.
So, first thing I would have thought of, but probably doesn't work, is just to add noise to the answer that you eventually, because it's queried.
Yeah, so
Yeah.
so actually, that's not a crazy thing to do in many settings. So there's even a name for it. You know, in the paper that worked on this originally, they called this output perturbation, where you add noise to the final answer. So that has provable. So actually, for with the median in general, that doesn't work well. And in some sense, the median is an interesting case, because in the most extreme data sets, the median is extremely sensitive to to even a single data point. And like for the median in one dimension, an example would be if I have half my data set at minus 100 and half my data set at plus 100, then the insertion of a single data point in either of those places will drag the median from one place to another. And so if you're going to add an amount of noise that doesn't depend on the data, then you have to add a lot of noise to have the worst case guarantees of differential privacy. So there are a handful of approaches that have been proposed to this. One of them is to kind of compute an amount of noise that makes sense for a given data set. So that it turns out you can do that, and it works reasonably well for the median. But then for more general loss functions, that calculation becomes complicated. We don't have like a general way to do that. Another approach is to add some kind of regularizer that makes the problem strongly convex and necessarily distorts the answer in the worst case. And in general, that works worse than the methods I was just describing. But there are certainly cases where it works just fine. So yeah, I could have had that on the list of sort of ideas people have definitely thought about. But again, for these optimization problems, so what these other methods I've talked about, in some sense, they adapt more naturally to the particular data set you have, and so that's why they seem to perform better in general. But yeah.
Another comment is that if your loss function is log concave, then you can include maximum likelihood in your store.
So I guess all of these loss functions.
Density, if you assume it's a random sample with a density that is log concave.
Yes, so all of these examples I have can be thought of as maximum likelihood estimators for some model that is whose density is log concave. Wait, is that true for a support vector machine? Okay, so definitely true for the first three.
I don't know about you.
Right. Yeah, so I would say what this is a, the kind of formulation I had on this slide, where is it? This, this one, yeah, is more general than that. So in particular, the MLE computation for any distribution with log concave density fits this framework, but this captures other things that don't exactly fit that framework, although I think most of the interesting applications correspond to that setting. So, yeah.
Yeah,
Jerry.
So I know you talked about convex optimization, but are there any techniques that also provide standard errors for some of these models, like linear regression?
That's a great question. So that work has started to be done. I mean, I didn't talk about that. Yeah, so for very specific problems, people have looked at algorithms for that also provide sort of standard error estimates and even goodness of fit measures for for each of your parameters, and sort of that provide this other associated information that you'd like to use for inference. And in particular, there's a nice recent paper by Or Shefet that does this for linear regression. And and there are probably a couple of other papers that look at sort of related issues. So certainly goodness of fit has been looked in a couple of places, in particular at Safi and Sesha and Steve and I have and Jinglei, sorry, have a paper that looks at that also, goodness of fit measures. But I would say Shefet's paper is a nice place to start. But I think that's maybe a good sort of general direction that lines up with something I said at the end of the tutorial yesterday, which is that for now a lot of the research is sort of very computer sciencey in perspective. It really focuses on sort of finding, minimizing prediction error and things like that. But providing additional information and also the sort of algorithmic tools to make good use of what you're getting for statistical purposes, that I think remains. There's a lot more to be done on that. Yeah. Any other questions? Yeah.
Could this framework cope with modelling situations where you've got some sort of feed through, like path models and structural equation models? Is the parameter estimation still good in principle in those circuits?
When you say path models, do you mean like
chain regressions, or so you're not just getting one set of estimates, you've got a series of things you're trying to predict which are interdependent?
Yeah, I don't know. So one can think of these iterative methods that I was mentioning, like noisy gradient descent or noisy Frank-Wolf, as providing sort of a number of points along some optimization path. Whether or not that same analysis extends to all such questions, I don't know. My guess is probably not. One can probably come up with things one would like to do that don't, for which the existing tools don't do a great job. And yeah, another question.
Just following on that, you've got lots of complex data structures, for example, hierarchical data, where you don't have decomposability. So I would assume that these methods don't apply.
So these methods actually apply to something a little more general than decomposability. So what they tell you about are any context where the loss function, the effect on the big loss function of any one data point can be bounded. But you are certainly correct that there are models out there that don't have this property, or where we just don't understand how a single point really affects things. So the example I'll give you is, which is topical these days, are these multi-layer neural networks, where the loss function you're optimizing has some crazy shape that we really don't understand at all. And to the extent we can do optimization for these models, fit these models, it's it's far from a science. It's even forget privacy, like we barely understand what we're doing. And I don't think I'm projecting when I say that. I think, so certainly I barely understand what's going on there, but I think that's a more general statement. So yeah, I think for more complex models, we don't necessarily have a good handle on how to reason about them. But so there are some models for which these techniques do apply that are more general than decomposable loss functions. But again, essentially what you require is a good understanding of how a single data point perturbs the gradients of the loss function you care about. That's really what it boils down to.
Can I just follow that up? Because when you started out with the notion of sort of bounding the influence of particular observations through the form of the loss function, I was expecting some and the analogy between that and the definition of differential privacy, some greater connection between the two, that perhaps you are somehow working in tandem, both in the traditional sort of robust statistics approach to sort of bounding the influence of individual observations, but also in the way you are protecting privacy in terms of attacking the same sort of observations. But in fact, the approaches you described didn't operate in any way on.
So, no, I'd say there's definitely a strong connection to robust statistics, and it comes in sort of. So the way where it comes in is sort of how this loss function is set up. So it turns out that these methods work really well on loss functions whose gradients are bounded, and that is a kind of an oversimplification of robust statistics. But basically, that's what these methods that people have come up with for various models that are robust. Very often, what they're doing is they're messing with the loss function to bound gradients, and precisely to bound the effect of any one person. So there's actually a strong technical connection between these results and the results from robust statistics, and an even stronger sort of philosophical connection. And there's another technical connection which I didn't get to, and which will come up in Aaron's talk, I think, which is that, so differential privacy is a form of robustness or stability. And what's been known for decades now is that algorithms that are either robust or stable in one of several ways have very nice properties in terms of how well what machine learning people call how well they generalize. So how strong a connection there is between the empirical risk you observe on your data set and the population risk, which of course you can't observe directly. Well, you can try to via cross-validation and methods like that, but in general you can't sort of directly observe it. So what you'd like are methods which give you a guarantee that if they do well on the data, then they will do well on the underlying population. And robust methods have these types of guarantees, and stable methods have these type of guarantees, and in particular, differentially private methods come with these guarantees.
Well,
yeah, so
that's very helpful, and I think I've let it run on slightly, so I think we better close there. So thanks very much again.
Thanks.